Hi, everyone. Thank you for joining today. My name is Anastasia Mityagina. I'm from the Lectures Without Borders. We are very happy to organize our first lecture for your institution in Nepal. And first lecture with us, also with Nicholas Cummins. I think it's the first one we do together. Please feel free to ask your questions in the chat. I'm sure that after the lecture part, there will be space for questions, and your questions will be answered, and I will take care that no question will remain unnoticed. So feel free to use this both in Q&A or in the chat as you prefer. And I will give the floor to our today's lecture.
Thanks for the kind introduction, and it's a real pleasure to be here today. Hopefully in the chat you can see I've put a link up which should allow you to download the lecture material. I apologize if it doesn't work, and I'll share the slides through Anastasia later today so you can get a copy of them. So just before we begin, just introduce myself a little. My name's Dr. Nicholas Cummins, or Nick as I'm commonly known, and I'm a lecturer in AI for speech analysis for health at King's College London, and I'm also the Chief Science Officer at a startup called Timea. My research interests are in speech analysis for healthcare and affective and behavioral computing. So trying to use computers to understand human behavior, human emotions, and sort of relate that back into the healthcare settings. I have a bachelor's and a PhD in electrical engineering from the University of New South Wales in Sydney, Australia. And I've also done some postdocing in Germany before I made it to my current position here in London. And yeah, what I'm going to talk to you guys about today is machine learning and applications into medicine and healthcare. So where we'll jump straight in really with this and sort of introduce the broad concept of what is machine learning and why it's, I guess, a little bit different from more classical forms of computer programming. And if we start with that, the more sort of classical form of computer programming, what we normally do is we have data and we want to process that data. We write rules that allow us to process. It allows us to find some information that we know might be in that data. The program we end up writing processes this data according to these rules and outputs us an answer. So we've got these three things here: data and rules, creating a computer program, and giving us an answer. And machine learning, we actually flip this around a little bit. So instead of having data and rules, we actually start with, a lot of the time, data and answers. So we have some, for my interest, some speech recordings, which are labeled with someone's level of mental health. And what I want to know is how to process them in the best way. And machine learning enables me to do this. So essentially, I supply a machine learning algorithm, data and answers, and it learns how to process these, and it outputs these rules. And these rules then allow me to process this data in the same way. So when I collect new data, I can process it again and again according to these same rules. So why do I want to do this? It sounds a little bit different. Why don't I just write rules for everything? And there's quite a few reasons here, but some of the big ones are time saving. It's actually really difficult to write straightforward rules for processing certain tasks. And the example I always sort of use here is just think of a cat, think of a dog. Inherently, we can look at these images and go, well, I know which one's a cat, I know which one's a dog. Now think about how complicated an algorithm you might have to write is to be able to tell these apart. So it's a lot easier, instead of just to use machine learning in this scenario, where it will learn what the important factors are between telling a dog and a cat apart and give us these rules that we want to know. And of course, when we apply this in medicine, these tasks get more complicated, more difficult to identify these rules. So in identifying these rules, what we're actually identifying is patterns in data. These patterns might not be obvious, and they might contain some really, really useful information for us. And in medicine and healthcare, this useful information could be diagnostic, it could be preventative, it could be some really important, almost life-changing information within these. And it's really difficult. We might not know how to process certain amounts of data or a lot of data. We just, as humans, can't process it. And this is where machine learning is really powerful. And of course, the more data we give machine learning algorithms, the better they get at making decisions in theory anyway. And this enables us to continually improve, make better and better decisions, or at least that's what the aim is. And again, why do we want to do this in healthcare? And essentially, if you think of a health system, data is everywhere. Every time we go to the doctor, we log data. Every time we look information up online, we log data. There's data everywhere, all over this. Every time we get a particular test, we might generate some images. All these things, there's data everywhere in the health system. And machine learning enables us different ways to combine a lot of different information sources, a lot of different data sources to do some of the main things: improving diagnosis, triggering earlier treatments in people, which is a lot of the research I try to do, discovering more effective treatments, better ways to utilize the data that we might have. So there's a lot of different things that we can actually do when we start to apply machine learning into medicine and into healthcare scenarios. Treatment recommendation is one thing that is often seen in the literature, trying to find the right people to fit in the right certain path that they might need to go through to get the best possible outcome within a health system. Mining some data to find candidates for different sorts of surgery that might be the best surgery they need, or trying to find candidates to avoid unnecessary surgery at the same time, using lots of data. So what we want to do with these things is sort of move beyond, the reliance on doctors who get it right a lot of the times, but also are still subjective. They're still human. And when we use this information, we can actually start to find objective things, better ways, just different ways of aiding medical decisions to help create the right treatments for people. And of course, we can even broaden this out and think of things like virtual therapy sessions. So having agents that people talk to, and these analyze speech signals, voice signals, things you might not think are necessarily medical signals. They analyze all of this to guide therapy sessions and aid therapy sessions. So there's a lot of different uses out there and a lot of power for using artificial intelligence, and in particular machine learning in healthcare. And what we're going to do over the next few slides now is sort of break down different types of machine learning that come up. And then I'm going to go through after that and just introduce you guys to the first few sort of big algorithms, common algorithms that occur, and just sort of hopefully give you some insights into, if you want to start to go and apply some of these, some of the best ways you can actually do that. So there's actually three main forms of machine learning, but this lecture I'm only going to focus on two of them, known as supervised learning and unsupervised learning. So supervised learning is the scenario I described first up. We have data, we have answers, and we're trying to predict that data, that answer, that label, is often what we call it as well, from the data. So we do this in sort of classification or regression tasks. That's where we use supervised learning. The other main form is unsupervised learning. So what we're doing there is we're just applying the data into a machine learning algorithm. What we're doing now is, instead of saying find an answer, we're pretty much saying find me something really, really interesting in this data. Find me a pattern, find me a trend, find me clusters of patients that might be there. And then we try to interpret this information that comes out of unsupervised machine learning. The third is reinforcement learning, which is a very different sort of form of learning to the first two. And you're looking at reward-based interactions with an environment. And I'm not really going to cover this in this presentation for the sake of time. It's a lot of new things, a lot of different things. Supervised and unsupervised just go together a little bit more, but reinforcement learning is definitely still there. So supervised learning, as I said, we learn from labeled data. The model input is data and an answer, so some form of clinical outcome. And we learn how to predict the answer. So we do this for tasks such as classification and regression. So you can see in these slides, what's happening is we have lots of samples of cats, and essentially we try to learn what's a cat, what's not a cat, and then label things through this in the supervised learning. And we do these tasks classification, so we're sorting into categories, sorting it into cats or not cats, or regression, so we might be trying to identify a particular trend in data, such as severity of a particular medical condition. So these are our main outcomes within healthcare, within medicine: prediction and diagnosis. So trying to say does someone have a particular condition or don't they? Or we're trying to might be saying something like how severe is a particular condition that they have. And then we have the unsupervised learning. So we're trying to learn from unlabeled data. We give the model data only, and we're trying to identify patterns, clusters, trends within this data. So here we're giving the machine learning algorithm images of cats and images of dogs. And what we're trying to do then is go, hopefully, group all the similar cats together, group all the similar dogs together, and we have these clusters. And what we might do with this is clustering, finding similar groups of patterns. So this could be some sort of population subtyping. So in something like mental health, we might be looking at grouping together people who have similar mental health conditions or need similar styles of treatments. We also might do anomaly detection. So if someone if we're tracking people sort of using wearable devices, is someone having a relapse in the condition? Has their pattern of behaviors changed, and does it relate to a change in their mental health? So these are sort of things we do here: cohort identification, detecting abnormal events, detecting change in routines that might come and indicate some sort of change of health status or population subtyping. So a lot of really cool things we can do here with sort of supervised learning and unsupervised learning. And now what I just want to do is take a little dive a little bit deeper, just really wrap our heads a little bit more around supervised learning, because it's really the main one and the one that comes up probably most in the literature. And what we're doing in supervised learning is transforming data into knowledge. We're learning to convert what we observe in an environment into what we want to know. So how we're doing this in sort of my research is we observe things like speech signals. And what I want to know is the presence of some pathological disorder, some presence of depression, some presence of some other condition that might be happening. And I will always use supervised learning to do this. So how do we learn in this sort of scenario what's happening here? So the first up is we need to collect data, and preferably lots of data when we can do. And we need to have matching labels with this data. So we'll work through a simple example. I have collected lots of images of cats. I've labeled them with cats. I've collected lots of images with dogs, and I labeled them with dogs. So now I've got this, I've got my data, I've got my answers. Now I need to learn these rules to sort this out. So how do I go about doing this? It's essentially a bit of a trial and error thing. I have a particular algorithm I choose. And what I try to do is choose an algorithm that suits the data I have. And I put in an initial set of parameters, or it randomly chooses an initial set of parameters. And essentially I take an image of a cat, I feed it through my model, and I go, did you get it right? Oh, it got it right. I don't need to change my internal settings. Oh, it didn't get it right. I need to update my internal settings. And there's lots of rules, lots of ways we go about doing this and guiding these updates. But it's the same sort of set of principles. We have an initial model, we pass some predictions through it, we compare how well it did, and we use this comparison to help us guide the updates so they step through and get better and better and better as it gets exposed to more pairs of data and answers. We compare with more targets, we can update these settings really well, and eventually we train this model. So we've got our final sort of settings. We go, this is the best I can do. I've got all my cats and all my dogs, they're nicely separated out. I've made a nice decision here. So I can get a brand new piece of data and go, oh, here's a new piece of data. I don't know what's happening in here. I can feed it through. And now I go, well, it's a cat. That's great. So I've got this new knowledge here built into these machine learning algorithms. And of course, we move on from cats and dogs into medicine. We might use images, we might use medical health records, we might use data from wearable devices, EEG data, all sorts of things to make these decisions. So finding these patterns, choosing these algorithms, you know, the complexity of the machine learning algorithms and everything steps up a lot, but these basic rules are always the same. And one of the most big steps, I guess, in machine learning, and one of the, I guess, more difficult things to sort of wrap our head around when we're doing machine learning algorithms is we're doing machine learning. We're not doing memorizing. So maybe some of you have done things like optimization techniques in mathematics, and literally what I've just described to you is an optimization technique, trying to get better and better at doing a decision. When we're doing machine learning, we actually don't want to get on our data that we're training our algorithm with. We want to make sure we don't go perfectly with it, and we don't want to learn absolutely everything, because we start to focus in on really fine detail that might just be within our training data, and we start to actually get worse at making decisions. And so we've got these concepts here that I'm going to introduce: training error and generalization error. So when we're training our machine learning algorithm, we're having the difference between our actual target and our predicted target in our training value. And we want to, of course, minimize this. But at the same time, we need to keep a little eye on what's known as the generalization error. How well is my machine learning algorithm doing on new data instances? And this represents how well our model is going to do when we go and drop it into a clinic, when we go and put it somewhere in real life. And we need to trade off these. How well am I doing on my training error versus how well am I doing on my generalization error? And what we generally find is if our training error gets too small, our generalization error gets worse. We actually go worse on new data instances. And I'll break this down a little bit more as we go on to a few more slides and explain it a little bit more of what's happening and why it's doing this. But it's this trade-off we've got to remember between these sort of two error sources. And how we do this trade-off is tuning machine learning algorithms. There's lots and lots of internal parameters that need to be adjusted, and how these are adjusted, these are known as model parameters, and how these are adjusted by sort of core hyperparameters that control this optimization process, that control this training process, and make sure that it's not learning too much, and helps us understand when to stop learning. So we learn the essence of patterns. So in these last slides, I've seen, you know, we're trying to learn these outlines of this difference between what's a cat, what's a cat and what is a dog, without actually going in. Maybe our training algorithm for our training data, for instance, has black cats and white dogs, and machine learning is not that smart. It might just learn, well, that's black and that's white, and therefore they should be in separate classes. And what happens then when we get a white dog or a black cat, it's going to be put into the wrong thing because we've learned the too fine a detail within here, and we've got to be very, very careful of how we go about and how we adjust all of these things. Essentially, what we're doing as we're learning is we're always trading off the errors, essentially, that these machine learning algorithms are making. So there's two main sources of error when we're always doing machine learning. One is known as bias, and the other is known as variance. So a biased machine learning algorithm, basically, every time we do a prediction, it's offset by a certain amount. So similar predictions might be predicted wrong, but they're all predicted wrong by the same amount. And then we also have variance errors, and the difference here is like we have a lot of similar instances, but when we do our prediction, all the errors are spread sort of everywhere within it. So it's basically, is there some sort of systemic offset in the errors, or are the errors spread out? And we're basically, when we're tuning machine learning algorithms, we're actually trying to trade off these different forms of errors, and we're trying to stop different forms of generalization errors coming through. So we have generalization errors where we're underfitting. we don't learn enough in the data. We lack sensitivity to any sort of variation there, or we go through for overfitting. And I'm going to come back and revisit these concepts a little bit more in a few slides time and jump back into this. We'll just dive deep into these areas here. So what we want to do is make sure when we're actually doing our learning is that we're avoiding, we don't learn too little, we don't learn too much, we learn just the right amount. And sometimes this means our system has to make errors. And this is really important, of course, in medicine, because we need to understand these errors and know what's being made, know the limitation of the algorithm, know the reliability of the information that we're pushing forward. And how do we do all of these with this idea where we're doing, how do we do this? How do we train this? How do we make sure we're avoiding all of these weird sort of errors? When we're doing sort of any form of machine learning, essentially what we have to do is we always have to train our algorithms and we always have to test our algorithms. So a training algorithm is basically, we get our initial data sources, we pre-process our data, we extract some information from it, we train our model, we have our model. So this means that we're making sure that we're minimizing our training errors. And then we test our algorithms. We go through, we get some brand new data sample. We do the same processing steps on it. We do a prediction on it. And we basically go, how well is our machine learning algorithm doing? And it's this sort of score, this final testing score that we're really interested in. We're getting good results there. We know that we've made a good algorithm that's suitable to go and drop somewhere into a clinic or make use of it or do some further investigations onto it. So just seeing there's a message dropped into the chat about what is supervised learning. So supervised learning is basically when we use data and labels. So we might have taken some recordings of, we might have some medical records associated with a particular neurological disorder. So we're mining for information and we're saying, does this person have or not have a condition such as epilepsy or a condition such as multiple sclerosis? So we get historical records. We know that this record, this data is associated with that medical condition. And we're trying to learn that there. And that's what supervised learning is. Unsupervised learning is when we say, oh, we've got all this data here, find me something interesting in it. Supervised learning is going, okay, we know that there's a relationship in this data. Please find the best way to get that relationship out. So I hope that sort of settled that out a little bit more. When we're doing training and prediction, we've always got to remember we've got to split our data and make sure that our data is set up in such a way to make sure our system generalizes the best possible way. And what we normally do is either split it one way where we have lots of data position, where we might use about 60% of our data to 60% of our data to train our model, 20% to validate it, and then a further 20% to actually finally test and go how well it's doing. If we don't have as much data or we want to look at a different way, we might use something like leave on out cost validation. So we remove a little chunk of our data, we train with the rest of it, we test on that last bit, we put this chunk back in and we take the next chunk out and we sort of keep moving this through. So yeah, it's quite a few different things here and we're going to revisit these particular themes as we sort of come back through and into the few more slides. But what I want to jump a little into now is this idea of actually how do I design a machine learning framework? How do I choose a few different things? And this should allow you guys, if you do want to go away and do some machine learning, to actually sort of know what to do, to jump in there, to take those first few steps. And I'm not going to explain everything in the notes just for the sake of time, but as I said, I'll give you guys these notes afterwards and hopefully they're a great resource for you. And of course, my contact details are there on them as well. So if you do have further questions, happily jump in and ask me a few sort of things via email, via Twitter later on. So the first thing we need to think about when we're preparing data to do machine learning with is how much data do I want to provide my machine learning algorithms? If I provide it, data from EEG, data from health records, data from x-rays, data from this, data from that, and try to give it way too much information, it's actually really, really difficult for it to learn. So we want to find the sort of optimal amount of information to feed into it. If I say, oh, I'm just going to say this person got score X from a blood test, that might not be enough information. But if I'm going to say this person got score X from a blood test, score Y from some other test, here's their EEG results, here's this, here's that. Of course, as I said, we add all of these up, we get too much. So we've got to make sure that we give the right information into a machine learning algorithm. And this is the idea of data preparation. We're choosing the right forms of information to feed through. So there's various different ways of doing what's known as feature selection or dimensionality reduction to help us ensure that we're feeding the right lot of information through. Because it's important to go, okay, as I said, have this correct amount of information, give the machine the best chance it can learn. And there's lots and lots of different ways we can sort of do this, and lots of different things where we could look at the statistical properties of the data and find the most relevant pieces of information in there first, and then feed them through to the machine learning algorithm. We could do how we select the data embedded in sort of a loop with the machine learning algorithm. This is wrapper techniques. Or we could actually have machine learning algorithms that actually perform and identify the best pieces of information to go with them. But of course, everything has trade-offs between these sort of underfitting and overfitting errors, and all these different machine learning algorithms come through with it. So yeah, this little thing here just sort of summarizes what I was talking about. If we're doing feature selection, we might filter our data first and use some sort of correlation algorithm, some sort of Pearson's ranking algorithm to go, what are our best set of features? We might actually go, here's some information, I'll choose 3, see how well it goes. I'll choose a different 3, see how well it goes. I'll choose another 3, see how well it goes, and sort of do this trial and error to find the best way. Or we might do something like deep learning algorithms, which we'll talk about a little later, where we sort of go and we give lots of information, and then the model will eventually learn which information is the best for it. So in the notes, I've put in some different reading materials. They go from the sort of high-level introductory blog to the best form of to a couple of papers there as well. So there's different levels of information for you guys to go through there. So other things to consider when we're actually choosing machine learning algorithms, there's quite a lot to sort of think about in here. The model's predictive power is one aspect of it, and this relates to the sort of complexity of the model. More complex model, so the more number of parameters it has in the middle of it, the more power it has. But we have a trade-off here with interpretability. The more complex a model is, the less interpretable it is. The more complex a model is, the more data it requires to train it. Then we've got things like how long does it take to train? How long does it take to make predictions? There's a lot of things we need to consider about the right way to actually choosing a machine learning algorithm. And a lot of this is about jumping in, about doing some programming, about learning these yourself. There's not actually many rules in machine learning that go, given this data source, what's the best algorithm? Unfortunately, we'll talk about it at the very end of the lecture. There's no one good algorithm, and a lot of it is just doing a lot of experimentation yourselves to actually find the best ways to do this with. And of course, sometimes we also need to think about the requirements with it. If we want to do some conventional machine learning algorithms, which what we'll talk about first, we don't actually need much data. If you guys want to do deep learning, you need a lot of data. And the other thing we need to consider now, and we'll come back to this idea I spoke about earlier, this trade-off between bias and variance errors and model complexity comes into it, of how long we want to spend sort of tuning machine learning algorithms. And every time we choose a particular machine learning algorithm, we're actually wanting to minimize, as I said, these generalization errors, these errors on our test set. So once we've trained our algorithm, how well does it go on new data? And we want to make sure that the errors on the new data are minimal. And how we sort of do this is we might start by choosing an algorithm that's not particularly complex. So linear regression, being a form of machine learning, is not a particularly complex form of machine learning. It's a layer of weights that we've got to learn. And we might find that actually, because it's not a particularly complex model, it generates high bias errors. So there's this systemic offset in our data. So we might go, oh, I might choose something a little more complex. I'll add some more complexity to this. And if we start to add complexity into the modeling algorithm we choose, we find that our bias errors drop. We find that our bias errors start to drop, and our variance errors start to decrease. So our model gets better and better at learning something in our training data. But as we get better and better at learning something in our training data, we get worse and worse potentially at our new held out test data. So we've got to find this midpoint where, given the size and source of the data I have, what's the optimal model complexity to make sure that my generalization errors are low. So we want a more complex model because they've normally got better predictive power, but we don't want to go too complex where we're doing memorizing, where we've optimized. Instead, we just want to make sure that we've actually got the right complexity of a machine learning algorithm, given the data we have, given the task we want to do. And we normally start, and I always recommend people start with a not complex model, quite a simple model. And generally what will happen is the model will underfit in this scenario. And as I said, this is where not learning the problem. We have our training set, we don't do well on that. We have a test set and we perform badly on that as well. And this is easy to address. We just choose a more complex model. And as we start to increase the complexity, we see these performance changes here. So that's quite easy to achieve. And we want to stop before the model starts to overfit. And this is really important. When we start to perform really, really well on the training data, but really poorly on the new data. And if we get into this scenario, it's actually quite difficult to overcome. We might need to choose a different algorithm, but it might not work. So we might need to collect more data, but this cannot be practical in some circumstances. If someone's undergoing really expensive medical tests, for example, it really might be difficult to go and collect more data. So, and this sort of understanding of these errors, and the reason I've spoken to you about them, and the reason I really spend quite a lot of time introducing them, is that one of the greater challenges in machine learning, and this is what we actually spend our time in doing machine learning research, is choosing the right algorithm to avoid these errors, to find the best possible model. We spend a lot of time going, is algorithm A, change some parameters, retest it, change some parameters, retest it. Okay, now I'll try algorithm B, same thing. And it's a lot of comparisons between different algorithms that may or may not work well on different data sources. And as I said, it's a lot of testing and comparison, because there's no real rules that say which algorithm will work better in any one particular circumstances. All algorithms have their advantages, have their disadvantages, and the best algorithm, machine learning algorithm to choose is the one that works best for your data. So understanding this idea of underfitting, overfitting, trading off between bias and variance errors in machine learning is the real heart of the research, especially in applied machine learning and doing applications into medicine, that we need to understand and that we need to do. And I'm going to briefly introduce a few sorts of supervised machine learning algorithms. So as I said, supervised learning, we've got our answer, we've got data that comes with an answer, and we're trying to learn between the data and the answer, learn these rules. And this is what all these algorithms will do. But I'll also briefly mention one unsupervised learning algorithm, which is the idea of clustering, where we're trying to find useful patterns within the data. So the first algorithm I'm going to teach is what's known as the random forest algorithm. And I know it says decision trees here on the slides, but we'll sort of build out to this. So a random forest is actually a collection of what are known as decision trees. And decision trees are one of the more simpler forms of machine learning algorithms. They basically are a series of choices where the data is split based on informative splits that give us the best entropy and trying to find different patterns here. So we got these different patterns between these sort of underlined and different numbers and different colored numbers. And we're trying to find the ways to split these out. So we've got our reds, we've got our zeros, we've got our ones, underlines, and our noughts, and we just try to find these patterns. Decision trees are really powerful because they allow us to visualize patterns, but this power is not actually that good. They're not very complex in how they make decisions. But when we start to form a lot of decision trees together, we can actually find, we can slightly overcome this generalization errors when we have a lot of models that don't perform particularly well. So what I mean by this is that we go, okay, I've got a model, I know it's got a bit of bias in it, but it's still making a slightly informative decision. It's still classifying at, 55, 60% accuracy. And essentially, if I get a lot of these models, sort of put them together and then average their results out, what I'm hoping is that they're all making errors. They're all making slightly different errors. So when I combine the good information from them, I've actually got something that's really, really powerful. And this is when we go from a single decision tree, which is never a particularly good model, to a random forest, which is a particularly powerful form of doing some fairly straightforward conventional machine learning. So we have this ensemble of different decision trees. If we're doing classification, we might do a vote. If we're doing regression, we might do an averaging output. And we reach these sort of final decisions. And it's a super powerful way of doing machine learning. And one of the first ones I always recommend people try. They're pretty quick. They work well on my data sets. They actually inherently do a bit of feature selection with us. But they're still sort of a little bit susceptible to sort of overfitting. There's a bunch of different things you need to tune in terms of the tree and the shape of the tree and how it relates to that. And this is what sort of explained in these notes. And the sort of quite a well-established Python toolkit to enable you to jump into it and to sort of get started. So scikit-learn has a lot of different sort of ready to go out of the box machine learning algorithms, and the sort of hyperparameters that go with them as well are quite easy to tune and easy to understand. The sort of next really classic machine learning algorithm, and you'll see it a lot in the literature and it's always a really good one to learn, is what's known as a support vector machine. So it does classifying. It essentially separates out data into two groups. And it tries to find where's the best possible spot to put this split between the two groups. And it identifies the data instances that sit closest to this boundary. And these are what are known as support vectors. So these are the data instances that are absolutely critical in making a decision. And it's using classical optimization techniques to try to find these training instances that sit absolutely as close as possible to this decision boundary. Let's say, for instance, one of these was removed, the whole decision boundary moves. But it identifies these small subsets. If you remove one of these outliers, it doesn't actually affect the decision boundary. It needs to know these ones absolutely closest to them, and that's what known as support vectors. And it actually allows us to make fairly complex decisions by having a bit of a tuning function that essentially allows us to put some bends, put a bit of variation into this tuning algorithm. So, sorry, my mouse keeps on just jumping around a bit today. So it allows us to essentially make small amounts of error, allows us to account for variability within the decision boundary. And this is known as the cost parameter. So when you start to do support vector machines and start to look at different algorithms, this is one of the big ones that starts to come through, the cost parameter. And basically that's where you start tuning support vector machines. It allows you to make different mistakes in the data and allows you to tune it a bit. And you do this in tune, as I said, with cross-fold validation or with leaving some data out in this sort of train, validate, test. Support vector machines have good generalization, they're pretty efficient, and they also allow the sort of decisions in both linear and non-linear spaces. So it's what's known as a kernel trick, where we start to put in different kernels, different transformations into the support vector machines. So the idea is basically if data in one dimension, if we can't see data in a separation in one dimension, if we actually transform that data into a higher dimension, things will start to separate out. And that's the idea behind the sort of kernels. And again, there's lots of things when we start to jump into the support vector machines that we need to consider: this cost parameter, this choice of kernel, and again, how we set about going and doing that. sklearn in the Python toolkit, again, has support vectors, has all of these instances associated with them. Again, there's a bit of reading material here to allow you guys to go a bit slower, go through this material and sort of figure out how these machine learning algorithms work. So just going to change tact really quickly and introduce you guys to one unsupervised machine learning algorithms. So supervised learning, data, label, and learn how to go between the data and the label. Unsupervised, data, find me something really, really interesting in the data set. And one of the most classic ways of doing this is essentially known as k-means algorithms. And this basically is saying, I think there are k number of clusters in my data. Please go and find these k clusters of data. So it essentially goes, okay, here are k potential starting points, assign things into clusters. Are these the best aligned clusters? Yes or no? Or I've got to make some minor adjustments. And slowly these sort of center points move and stabilize over time as we sort of go through these training instances. So we might start and go, okay, there's 2 clusters within this data. We can sort of see how that would nicely line up. Actually, there might be 4 clusters, and there's ways you can measure the ideal number of clusters versus the number of data that we have as well. It's a fairly easy algorithm to works well on large data. But yeah, we do need to do a final bit of tuning to actually know what the number of clusters is. And again, sklearn through Python has a lot of this here. And again, I've just put some links to some reading materials through the notes for you guys. And again, any sort of questions later, please don't hesitate to reach out to me on email, on Twitter, and definitely get back to you guys. So the last thing I want to introduce, which you guys have probably heard about in terms of artificial intelligence and machine learning, is of course deep learning. And deep learning is basically the hottest, the most popular form of machine learning currently out there. It's the one that's getting the most hype in the media when you see it a lot of the times. This is what's happening, this is what people mean. But deep learning is a subform of machine learning, highly actually similar to something like linear regression. But it's called deep because in something like linear regression, we just learn one set of weights to go from data to an answer. In deep learning, we're actually basically stacking a set of these transformations up one after the other. So we go, I have my first set of weights to transform the data. I then transform the data and I feed them into a second set of weights, and I feed them into a third, a fourth, a fifth set of weights in these different layers. And that's where the turning deep comes from, because we have these multiple sets essentially of linear regressors. It's a little bit more complicated than that in through these, and we eventually learn how to make a decision. And it's a really powerful way of doing machine learning, because essentially we're doing machine learning on machine learning on machine learning. And if we have enough data, this really does often help with us. But we're not quite doing exactly linear regression each time, because if we just stacked a whole load of linear regressors together, we're not actually doing anything super informative. What we do is, buried in these outputs, we actually do what's known as a nonlinear transformation. So we start to learn how to turn different outputs off, or just scale different outputs as they're coming through each particular layer by a certain amount. And this induces nonlinearities, and this allows us to learn really super complicated things through each layer of transformation as we go through. And we can do some sort of really cool processing using these. And two forms of deep learning that come up a lot in the medical literature are convolutional neural networks, which are just a way of setting up and learning how to filter. Essentially, images is what they're mainly used for a lot. So if we want to do something like lesion or tumor detection coming from images, we'll use convolutional neural networks to do this, and essentially just learns how to transform data over these big numbers of successive layers. And the other form we use is what's known as a recurrent neural network. And essentially, this is when we start to model time series. So we might start to monitor people over time and trying to look at how things change. We might use something like a recurrent neural network, which essentially has some memory in it that says what happened at the last time step and how does that affect the next time step. And we sort of move on from these. And so there's obviously lots to do, and lots of more complexity comes into machine learning when we start to think about deep learning. The reason we might want to do this is because it performs well on big data sets. So if we've got, hundreds and hundreds of thousands of data samples, at some point of time, algorithms like random forest and support vector machines essentially don't learn anything new from that data. They sort of saturate, and no matter how much more data we train them with, we only really get slight improvements in their accuracy. Within deep learning, we find that we can actually get better and better performances and scale the complexity of the algorithm to suit the amount of data we have to get better performance out of them. So that's one of the big reasons we do it. The other reason we do it is essentially what's known as end-to-end processing. So we're doing, people like me, engineers, sometimes out of a job when we're doing deep learning. So often we have data. And as I said at the start of the lecture, we often need to do some pre-processing. We need to do some learning of the information we want to feed into our machine learning algorithm before we do the prediction. Deep learning algorithms actually allow us to skip this step out, not all the time, but sometimes, and essentially it will allow us to go from our data, and we can essentially put it straight into a machine learning algorithm and actually form our final prediction. So it's a really powerful way to learn directly we can go from the data to our prediction and learn directly what we need from it. So yeah, it's a particularly interesting way and powerful way of doing machine learning. Online, there's lots and lots of reading materials out there. So I put a link to some of the best of them there for deep learning, for machine learning, and of course a link to some of the main toolkits that are used for it. And again, something definitely worth giving a go. One thing that we need to be really careful about, and especially when we're doing machine learning and deep learning in medicine, is how we actually score how well our algorithm is doing. How do we actually go, it's doing really good? And one thing we have a lot in medicine is potentially unbalanced data. So if we're trying to, for example, detect a really rare condition that might only occur in 8% of patients we screen, we can actually get a highly accurate model that's right 92% of the time by essentially saying everybody that comes in doesn't have this condition. Wow, it's a great model, it's correct 92% of the time, but that's not actually reflecting the real world conditions that we have. We're 100% correct for people who do not have the disease, but we're never correct on people who actually do have it, and they're the people we want to get correct. So it's really important that we think about how are we scoring our algorithms, and do I have the best scoring mechanism for the actual task that I'm trying to do? So am I trying to predict the total number of correct predictions? That might not be enough. We might want to look at things like the precision and the recall. How trustable is it when it gets a result right? How well can it detect a particular task, or something like the F1 score that sort of weighs these off? And I'd always recommend things like recall and F1 score are particularly important when we're actually doing something that's particularly unweighted or looking at particularly rare conditions. Because when we start to think about things like recall, things like precision, looking at what's known as a confusion matrix, so looking at where it's made correct and wrong choices in our algorithms, we know that if our machine learning algorithm is high recall and high precision, we're doing really well, you know. And when we're thinking all the way back to our trade-off in, as I said, we always want our machine learning algorithms, essentially we might always have to have a little bit of error in them. And we've always got to trade off and go, well, how are these making these errors? And precision and recall can allow us to interpret this a little bit more. We might set our algorithm up to have high precision and low recall. So it means it's not detecting something well, but we can trust it when it does. Or we can set the opposite sort of bar where we go high recall, low precision, and go, it's really well at detecting this rare event, but it's going to have a lot of false positives coming through it at the same time. So, you know, just sort of completing all these different loops here. We're doing machine learning algorithms. We're doing machine learning, so we've always got to have some errors. We've really got to understand how these errors are then propagating through, especially in medical applications where things might sort of change around a little bit. Of course, if our data is really unbalanced, we might want to think about sort of balancing up data by undersampling or oversampling. But of course, everything has these trade-offs coming through in there. So yeah, that's a really sort of brief and quick and over the top introduction to some of the core concepts in machine learning, some of the main algorithms to use. I'm just going to end with a couple of slides, again, for things to think of, especially as you're using machine learning sort of into health questions, and then I'll be able to take a few questions. So the one thing that I hope I've managed to stress here through this lecture is there's no real way of saying, you know, before you start doing machine learning, given my data, what's the best possible machine learning algorithm for it? Models are only as good as any assumptions or their sort of pros and cons with them. And this idea of simpler models having more bias, complex models having greater variance. So there's no good machine learning algorithm. The best machine learning algorithm is the one that suits your data the best. The only way we can find this is essentially empirical evidence. We need to try lots of different algorithms, tune lots of different hyperparameters in these algorithms, and essentially compare them, compare these trade-offs in precision, recall, whatever the metric is we're trying to use, and make sure we've got the right metric for the task. So we need to consider how we prepare our data, how we choose the right amount of information to feed into it. If our data is underbalanced, what are we going to do anything about that? Picking the right complexity of the model to suit the data. Making sure we're actually starting with a model that maybe a little bit simpler than what we need, so we can start to understand. If we start to, you know, if we've got a brand new data set and I go, I'm going to do convolutional neural networks on it, oh, look, it didn't do really well. The subtleties of why it might not went well are a bit harder to understand. So starting with a simpler model gives us something to compare to as we start to improve that complexity of the model. And of course, always thinking about the best ways to judge performances. And a few other things we need to think about, and this is more a going forward thing and challenges into healthcare. Machine learning algorithms always take shortcuts. They might look at different correlations, things that we don't quite understand. We can't presume that a machine learning algorithm has made a decision in the same way that we would have made that decision. It's going to make it in the simplest way it can see to make that decision. And we don't, as humans, understand that. We also know that there can be biases within the algorithms of how they work and biases associated with data. And we've really got to think about these, that we don't quite understand how the decision got made, and our algorithms can be inherently biased. So we always need to think about machine learning algorithms that are more explainable and more transparent, and understanding these ensures that we have fair algorithms, ensures that potentially things like privacy might be protected. They're reliable, they're robust, especially in medical settings. We know that the relationship's being modeled are causal, and all of this sort of comes together at the end to make algorithms that are a lot easier to sort of trust and a lot easier to train. So hopefully you guys can understand why I spoke a lot about different models, different errors, different ways of doing this. These are really important fundamental concepts to understand, especially when we think about the challenges of putting machine learning algorithms into health. So again, here's my contact details at the back of the slides. If you do have any questions later, please reach out for me. I'm happy to hang around for a few minutes now and take some questions. So thanks, everyone.
Thank you very much for the interesting lecture. I can see that we have there several questions in the Q&A box and also in the chat. Can you see those?
Yeah, I can see them. So I'll start at the top here from what's the use of machine learning in daily life? That's quite a big question. The honest answer would be probably not much. There's not actually many applications of machine learning currently in daily life that are particularly useful. So where we see machine learning in sort of day-to-day products, often consumer products, so things like Siri, things like OK Google, these are examples of machine learning in everyday life. How useful they are, I don't know. You know, if you're looking on things like Amazon, you know, your recommendation systems on Amazon, Netflix, all of these things are based on machine learning algorithms. They're where we sort of see things currently in daily life in consumer products. And I think the reason that we see them there is a lot of these things, it's not that critical if Siri doesn't understand us properly. It's not that critical if Amazon makes the wrong recommendation of the next product we buy. And we've got a long way to go in understanding that criticality, I think, of the decision, especially in healthcare, to make these work well. So I hope that's answered your question. So the next question up we had, how can we choose the appropriate algorithm for our data set? So anytime someone asks me this, I pretty much say, start at one of the simpler algorithms. I personally always start using random forests or using support vector machines and starting at that end and just sort of see, you know, set that up, spend a little bit of time there and get to know it sort of helps you, it's a weird thing, get to know your data, understand, start to form a relationship a little bit with your data. And you can do that easier sort of on these smaller algorithms that take a quicker to run, easier to understand. And once you're sort of confident that you've got a system working well on these, you can then start to look at more complex ways of modeling the data, then start to go, maybe if you feel you've got, you know, sizable amount of data, you can start to go towards deep learning and things. But yeah, the best place to start is always something like random forest support vector machines. Everybody sort of starts there and just play around with them a little bit before going more complicated. So the next one here, are there algorithms that work well for categorical and numerical features? There's not actually that many algorithms that work well for categorical features. So decision trees are one of the few that might actually work in these circumstances. What you find is the example here being something like language understanding, so natural language processing. There are very powerful ways of converting a word into a numerical representation of that word. And that's what's used a lot. And there's actually sort of deep learning algorithms that do this, go, this is a word and this is the numerical representation of that word in some sort of larger semantic space. And, you know, a lot of things are characterized that way. I mean, images themselves, when you think of an image, it's actually just a representation of different levels of color, and you're able to break that down into a vector very, very easily. When I do things like talk about speech processing, there's lots of different ways mathematically I can go from sound to a number. How loud am I speaking? What's the tone of my speech at any one particular time, what's, all these different things. So there's a lot of different ways we convert categorical or things that we might not think of numeric into a numeric representation before we do any machine learning algorithms. Essentially, most categorical things aren't particularly powerful, so we need these numeric transformations. How do you think quantum computing will affect machine learning? It's going to be very interesting to see how that trades off. I think it will enable more powerful ways of doing sort of deep learning, and how we can maybe represent data in different forms that are more powerful for algorithms to understand. I think it will increase the power of things, but unfortunately with that will probably become the main of big tech for a while, because, well, universities aren't going to have the resources to be able to really get the amount of data needed to learn these things, because they're going to essentially allow us to do more complex decisions, and with that we'll need more data. So yeah, it's going to be a while before, outside of some really, really well-funded research or some really big tech, that in sort of day-to-day life we see those big effects coming through. So does deep learning compare with other machine learning algorithms? So it essentially comes down to the amount of data you use. You have a very small data set, deep learning is not going to work very well for you, because you either are going to be exceptionally biased because you actually haven't been able to train it particularly well, or it might just learn this really weird thing, decision boundary. So it's not going to do well if you have a very small amount of data. But as you get more and more and more data collected, so, if you've got, 20 health records or 50,000 health records, on 50,000 health records, the deep learning algorithms are going to do a lot better, because you've got the amount of data there to actually support the more complex decision that's made with them.
Thank you so much. I can see another question in the chat. Could you please explain what is the difference between machine learning and computational statistics?
Yeah, this is always an interesting one. On some levels, there's not much difference. On other levels, there's quite a lot. So computational statistics is all about looking at how powerful a relationship is, in my understanding of computational statistics anyway. You're looking and saying, this piece of information relates to this phenomenon with a certain amount of power. You're going, okay, this is, there's some, you're essentially putting a number on the strength of a relationship. Machine learning, you're actually going, can this piece of information predict that label? So it's just a slightly different form of a relationship that goes with it. One is essentially going, what's the strength of the relationship? That's statistics. Machine learning is going, can I use this information to actually predict that output? And there's a bit of crossover. Something like linear regression is essentially doing both. It's either or there, but it's then, if you're interpreting the weights, you're doing statistics. If you're interpreting the output, you're doing machine learning there. So that, I think, sort of is probably the best way to describe the difference between the two.
Thank you so much. I can see we have also one hand raised. I will allow the person to talk. It's just a second. The hand was lowered. Okay, you can ask your question now.
Excuse me, I have a question.
Yeah.
Hello, Dr. Nicholas. Thank you so very much for your insightful sharing. Actually, I'm being a student of business, myself very interested in machine learning and artificial intelligence. I can see machine learning in medicine covers the techniques of machine learning and their application in the medical field. It actually presents several computer-aided diagnosis system, CAD system, which have played an important role in the diagnosis of several diseases in the past decades. including cancer detection, resulting in the development of several successful systems. So
Yeah.
what are the real world problems that can be solved using machine learning and artificial intelligence in the future? And my next question related, connecting with this is, what are the machine learning problems that have not been solved yet? Thank you.
So yeah, in medical applications, I would say the big advances of machine learning have been in sort of medical imaging, definitely, and being able to interpret medical images. And then I think some challenges in that area is sort of then feeding that information back into sort of real-time algorithms for helping plan treatments and things like that. I think that's in that sort of domain, we're very good at sort of helping clinicians reach decisions, find things in images. But I think the next challenge in that is sort of, okay, can we then start to recommend treatments and recommend that next, I think, step forward in time? One of the big challenges that I sort of work on a lot about machine learning and artificial intelligence in health is the idea of sort of preventative and personalized medicine. So can we use people's data to try to predict in advance what might be about to happen in their health? And can we sort of recommend steps to try to minimize the effects of that might be? And we do this a lot. I do this a lot in mental health settings. So, you know, we do lots of experiments where people wear wearable devices for days, for years at a time, and we're trying to learn sort of relationships between how does your change in the number of steps you do a day, the heart rate you do. We can gather lots and lots of information from people using fairly non-invasive techniques, and then try to go, okay, are you going to have a relapse in a particular condition? Can we see that coming in time? And then I think that's what we're currently working on. And the next steps from that are going to be, okay, how can we use this information combined with other sort of health records and health information to actually personalize treatments and recommend things for people to do to sort of take more charge of their own health and make better decisions together, I guess, with their own data and with their doctor at the same time.
Thank you. I believe we have one last question in the Q&A box. What do you think about cross-validation technique? Would you use on a time series data set?
I mean, cross-validation is probably the better way to do things, but it can take a lot longer if you have a lot of data to use cross-validation, because you're essentially using all of your data to train and test your algorithm so you get particularly well. I mean, on time series data, there's a few different things you can do. You can essentially, you know, take a bunch of time series and sort of split them and use one for doing training and one for doing testing. Or you can sort of use the first half of a time series and test on the second half of a time series. Or you can do weird things like train on the second half and test on the first half, and things to check how well your model's doing. So the same sort of techniques will apply on time series data. You can just think about how you want to divide them. And again, if you make particular decisions on how you use these time series data will affect the outcomes and potential biases in your data. So you just got to think, am I making a personalized model by using the same time series, or am I making a generalized model by comparing between time series?
Thank you so much. I think we are done with the questions for today. Deepak, you wanted also to use a couple of minutes, right?
Yeah. Instead of being very difficult to speak, I'd like to speak some words here because I found this a very insightful and wonderful session by Dr. Nicholas. So I thank to Dr. Nicholas on behalf of Texas College of Management and IT and Mathematical Association of Nepal, in which Lecturers Without Borders is partnered with, for taking time from your busy schedule to be the resource person in this webinar. I'm not actually showing my face because it looks ugly being sick for 5 days. So your presence and insightful sharing helped our students to magnify their knowledge horizon. All thanks to your enlightening words that inspired so many people out of there. I also thank you, Miss Anastasia, and Lecturer Without Border. Without you, this day was not possible. So I look forward to our next interaction soon in the days to come, and wishing you all the best and healthy days ahead. Thank you so much.
Thank you.
Thank you very much. Thank you everyone for being here. Thank you for the lecture. We hope it will be not the last one together with us.
Yes.
And I will be happy to share with you the recording, of course.
Thank you. And I'll share my slides back so you can forward them on as well.
Yes, perfect. Thank you very much. I wish everyone to have a nice Saturday and a good weekend.